Now, as long as processes do not interfere with each other, and if they are just running independently, like process P1 runs and process P2 runs, there will be no problem at all, which means I told you how a process looks like. Right? There is something called as this code, and then static variables, and then there is stack, and then there is heap, like this, right? This is some process and this is other process. Now what will operating system try to do is, or what will operating system always provide is something called as security, which means any process which is running is just supposed to use only the memory allocated to this. If process P1 is running, it is never supposed to refer to any other element which is not present inside this. And if process P2 is running, it is also never supposed to use anything other than this, right? So as long as this is the case, if operating system is providing you with the protection, that is called protection, okay? As long as operating system protects your memory space from the other processes, there will be no problem at all. But then there can be some problem if two processes are trying to communicate with each other. So why communication is a problem is, okay, so one thing here, when I am talking about processes in operating system, we are mainly concerned about the process which are running in the same computer or in the same host. But when we talk about inter-process communication in computer networks, see, what is computer networks? Completely inter-process communication. Two processes want to communicate with each other when both of them, when these two processes are in different hosts, right? See, so in computer networks, it is like this. Two processes are present in two different hosts and they want to communicate with each other. There we have used the protocol stack ISO, SI, TCP/IP for this inter-process communication. Now in operating systems, what is the main difference is, in operating system we are not going to use different computers. In the same computers, two processes want to communicate. For example, there is process P1 and there is process P2, both are present in the same computer and now they want to communicate with each other. Why do they really want to communicate with each other is, they want to cooperate or they want to compete for something. For example, maybe I have some task to do and I divided the task in such a way that P1 will do some work and then P2 will do some work, in such a way that P1 will finish its work and then P2 will take the output produced by P1 and work on it. And now when these two processes are running simultaneously, it will be a problem. Okay, again see this, P1 will produce some output and now P2 will take that output as input and produce the final output, right? And it occurs at many places, okay? And now if I have such a task, then both are cooperating to complete something, isn't it? Or sometimes they might compete for something, which means let us say P1 and P2 are two processes which are trying to access the printer. Both of them want to print something. In that case, P1 and P2 will simultaneously try to access the printer. That is called competing. So whenever they want to cooperate or they want to compete, they need to communicate, right? And whenever they communicate, they are going to do it with shared memory. Shared memory means like this, see? Now we can say that P1, you please write the output here in some common space. Let us say this is shared memory. In the shared memory, P1 is going to write something, and now from that space P2 is going to read it and then run it. Now as long as they are not running parallelly, which means if this is written in such a way that P1 will finish its writing, then P2 will start reading. If that is the case, there will be no problem. But then if both of them are running simultaneously in such a way that P1 is still writing the output and P2 is reading the input from it, simultaneously if it is happening, there could be some problem. And similarly, if both of them want to write something to the printer, then it could be like this. Both of them can put their data here, which has to be printed, and now some other process will take this data and print it. Then what happens in that case? Both of them might write the data at the same time in this memory, and because of that one of the data might be overwritten and it will get lost, right? Anyway, whenever two processes are trying to cooperate or compete, they need to communicate using shared memory, and whenever they communicate using shared memory, there is a chance that there could be some inconsistency, which means data inconsistency, or there could be some other errors possible. So mainly here data inconsistency is very possible, right? So I'll just take a small example and explain you what happens because of this shared memory. Assume that there are two processes P1 and P2 which are running in the computer, two processes P1 and P2, and now both of them are using a common variable count, right? Both of them are using a common variable, which means you can think that these two variables, these two processes P1 and P2 are having somewhere some shared memory to which both of them are given access by the operating system, and now both of them are communicating, right? And now assume that this is the variable count and its initial value is 5. In P1 the code is such a way that it wants to do like this. Let me say the code of P1 is like this. There is something here, and at some point P1 wants to do count plus plus, and now P2's code is such a way that P2 wants to do at some point in its program count minus minus. See, now the entire program they will not access the shared memory, only some part of the program they are going to access the shared memory or some variable or some resource. That part is called as critical section. So we shall see about it later. First let me finish this example. Now P1 wants to do increment the count in its code, and P2 wants to decrement the count in its code. That is how they want to access the common memory. One is incrementing it and other is decrementing it, right? And that is happening at some point in time in their programs, right? And now initially assume that the value of count is 5. Okay, this is the scenario. Now if you look at how this count minus minus and count plus plus will be converted to the assembly language code, I'm just writing it like this. So count plus plus might look like this. So it might contain 3 instructions at assembly language. First instruction may be we want to move count into some register or not, and second instruction may be after moving it maybe we want to increment the or not, and third instruction is we want to move or not back into count. Okay, so this is how the typical instructions look like when you are trying to increment a code. So there are some operating systems which are able to increment it atomically, but then most of the operating systems, most of the platforms, they support these 3 operations. So whenever you have this high level language code, one line, it is going to be converted into 3 assembly language lines, right? And similarly if you look at count minus minus, how does it look? So first thing is we want to move again count into some register. It need not be or not, or it can be or not. So whenever I'm talking about or not, it depends on the context, in the sense when some process is using or not here, and when it gets preempted and other process gets into running, then the or not value whichever this process was using will be saved in its memory. Okay, just not to confuse you, I don't want to confuse you here. So it can even be or not, the register or not, but I'm simply writing R1, right? So it doesn't change anything, it will just not create any confusion for you. And now second thing is decrement R1, and third thing is move R1 into count. So this is how count minus minus is going to be implemented, and this is how count plus plus is going to be incremented. In case if your operating system doesn't have a platform that doesn't have increment or not command, you are going to say or not equal to or not plus 1. Here you are going to say or not equal to or not minus 1, right? Anyway, these 3 instructions are going to be done. Now first one is nothing but reading, second one is nothing but changing or updating or changing, and then third one is nothing but updating. Reading, changing, updating, right? So when you have such a sequence of moves, what can go wrong is Now let's consider a scenario where we have this scheduling algorithms which are preemptive in nature. Preemptive means even when a process is executing, even if it didn't finish its execution, we are going to stop the process in the middle and then we are going to schedule a other process. Now in this scenario, what happens is, I'll just take this example. See this. Now what did I say? Initially the value of count is 5 and we have these 3 instructions. Assume this sequence. For some time, assume that P0 is scheduled, right? So what does P0 have? P0 have the P1 and P2, right? So assume that now the process P1 is scheduled, right? And now we are looking at P1 and we are assume that we are doing count plus plus, and so P1 is executing its line number 1, line number 2, line number 3 of this particular code, only count plus plus, right? Then what happens? Then we are going to move this count value into R0, therefore R0 will get 5 and increment R0, which means R0 will get 6, and then move this 6 to this, right? Then what happens if P0 gets 1, 2, 3, then this one is going to be incremented to 6, right? And then assume that P2 is got scheduled and now P2 executed its 1, 2, 3 lines. Then what happens? Then we are going to read 6 into R1 and then decrement R1, which means it will be 5, and then R1 will be written back to count, which means this will be 5 again, right? Therefore, if these two sequences occur one after the other, P1 followed by P2 without any preemption in the middle, then what happens is all the process, everything that will get printed is consistent in the sense the value of count is actually 5 and after count plus plus and count minus minus it will remain 5 again, which is consistent, right? But there could be something wrong, something might go wrong if there is preemption in the middle. I'll just show you a sequence because of which there could be something wrong happening. Okay, why only that sequence is, okay, why should you believe that if there is such a sequence is possible is, Graham's law say that if something might go wrong, it will. Therefore, if there is a chance that this might happen, then definitely it will happen at some point. So you should handle that case and see that there is no chance of that being happening. Okay. Now I'll just show you what could go wrong. Now if P1 executes line number 1 and let us say line number 2, then what happens here? So initially count equal to 5 and that count will be moved to R0 and now R0 will be incremented by 1, which means R0 will take 5 and now it is incremented by 1, which means now the value of R0 is 6. That is what has happened. Let us say at this point P1 got preempted and P2 got scheduled, right? And now P2, it has executed 1, 2 and 3, which means P2 will read 5 itself, right? Again move count to R1. It is interesting. See this? Even though P1, the value of count is incremented, whose value is 6, it is not yet written, which means the value of count still reflects 5. So whatever value you have incremented, that is not yet written onto the variable, right? So till this point, even though the value of count has to be 6, it is still showing as 5. At this point, the process P2 whose this whose code is count minus minus will try to access. See, we are assuming that both are accessing these two codes, right? And now we'll try to access count now, which is going to get 5 into this R5. This is the mistake which might happen. See, even though we have incremented the count, value of count, we are not able to reflect it there, and in the meanwhile some other process came and it read the value which is wrong, which is inconsistent, right? And now the this one count minus minus means, but first we are going to read 5 into R1 and then decrement 5. Second line is decrement R1, which is nothing but now R1 will be 4, isn't it? And now move R1 to count. Finally 4 will be moved here. Got it? And then it got preempted, and finally P1 has came into existence, and finally P1 is running the line 3. So what is it? move R0 to count, but according to P1, what is the value of R0 now? 6. Therefore 6 will be written, isn't it? Now check that. So because of this order of execution, so is this order of execution possible? Yes. No, it is possible, because if this kind of preemption happens, and preemption can happen at any instruction, isn't it? Therefore, if there is a chance that this sequence can happen, it will definitely happen in reality, right? At practice. Therefore, we should even handle it. So what happened? After executing count plus plus and count minus minus, the value of the count is supposed to remain at 5, but here the value of the count is showing 6, isn't it? Or let's say what happens if we do something like this. P1 is executing first line, second line, and then P2 is executing first line, second line, and then P1 is executing third line, and then P2 is executing third line. Let's see what happens with this sequence. So initially the value of count is 5. The value of count is 5. P1 is executing first line and second line. So P1 is this and P2 is this. So P1 is executing first line and second line. So what does it mean? P1 reads 5 into R0. Okay. 5 is here, and then P1 will increment 5, which means 6 is here. Fine. And now P2 is executing first line and second line, which means still P2 will also read 5, and then it decrements 5 and it will be 4. Now according to P1, the value present in R0 is 6, and according to P2, the value present in R0 is 4, right? And now if P1 first prints it, so if P1 first prints there the value, which means P1 is going to write R0 to count. It's not printing, it is storing. So P1 is writing R0 to count, then here it will be 6. And then P2 writes. If P2 writes R1 to count, then it will be 4, right? So now the value is going to be 4 finally. Earlier case, see, in this case count is going to be 6, and in this case count is going to be 4, right? And in this case count is going to be 5. So all these three values are possible depending on the order in which you are executing the instructions, isn't it? So if this particular execution takes place, which means if the preemption happens after this, like this, then the order is going to be 5. Or even if the other kind of execution, which means P2 1 2 3, then P1 1 2 3, then also the value of count is going to be 5. If this happens, then the value is 6. If this happens, then the value is 4. This is called as race condition. Race condition means the final output depends on the order in which the processes are getting executed, right? Which is actually which should be avoided. The actual value has to be 5, which is the consistent value. Now the actual value that is going to be stored is inconsistent, right? Why do you think that this has happened? The reason is very simple. Two processes are trying to communicate with each other, sharing a memory, and now there is this preemption, right? There is reading, changing and updating, and in the middle there is preemption. And when you have more than one process updating the variable by reading it and then changing it and then updating it, then there is going to be a problem, right? And in fact this part of the code, the part of the code where the processes are using a common resource, is called as critical section. Critical section. The terminology is important. Critical section. There are no theory questions on this. 1 or 2 are there. Mostly problems are there, but still you should know the theory so that we can solve the questions. Now what I am saying is the part of the code inside the process which will access the shared memory is called as critical section. Critical section means in that part of the code is actually accessing something common. Either it is a common resource or a common memory. For example, in these two programs, the common resource is count variable, and this is the part of the code which is using the count variable in these two parts. Therefore, this is the critical section in P1 and this is the critical section in P2, right? And now the final output is depending on the order in which the instructions are executed, which means depending on how you execute the instructions or how you preempt the process, or the which one wins. We call it race, right? So if P1 finishes first, see, if P1 finishes its execution first, which means here, then the value is going to be 4. If P2 finishes its execution first, then its value is going to be 6, which means there is a race between the process. Whoever wins the race is going to define the value, which may not be right? Therefore, this is called as race condition. Race condition means the output is depending on the order in which the process are executing the instructions, or the process whichever finishes first is going to decide the value of the output. In this case, if P2 finishes first, then the value is going to be 6. If P1 finishes first, then the value is going to be 4 in this particular order, right? So now there are going to be race conditions because of which the values are going to be inconsistent. Now what is the solution then? The solution is we should see that there should be some kind of synchronization. Synchronization means the entire process has arrived here. When one process is in its critical section, other process is also going into critical section. If you could see that only one process will access the critical section at any time without letting any other process access the same critical section during that time, we can see that we can actually stop this problem from happening. What I mean to say is, if either you let P1 to completely access the critical section and then allow P2, or either you let P2 to completely finish its work and then allow P1, that is called synchronization, right? And somehow if you could manage this, then such a problem will never occur, isn't it? Why? If P1 finishes it, then it is going to maybe increment the code and increment the value of count, and it will be 6. And then if P2 starts, then it will decrement the value, it will be 5. Or if P2 finishes it, then it is going to decrement the value, which will be 4, and then if P1 finishes it, it is going to increment it, then it is going to be 5, which means you should see that one completely finishes, then the other will start accessing the critical section. If you can see that happening, if you can make sure that it happens, then that is called synchronization. Now we are going to see the solutions or synchronization techniques using which we will ensure that only one process enters the critical section, right? So I'll just show you how it is done. Fine.